Hi, I'm Jason, and welcome to this section of the Chemistry Tutor. In this section, we're going to talk about units and unit conversions. And so don't forget, chemistry is a mathematical science. So yes, we're going to be talking about reactions and molecules and things like that, but mostly we're going to be interested in calculating how much of something happens. How fast does a reaction proceed? Is it a violent reaction or does it take years to happen? So we're going to be dealing with numbers. And so as a preface to that, we need to be comfortable with the SI system of units, which is the standard system that we use when we talk about chemistry and also physics and other branches of math and science. And so in order to do that, we're going to talk about units, and then I'm going to teach you one little thing here at the end, which is probably the most important thing you can learn as you start chemistry or any study of any science. It's the most important thing I know that has saved my life in terms of doing a problem many, many times, and that's how to convert units properly. It's so incredibly important. I cannot stress how important it is. Now, let me go ahead and say right now that this section right here is going to be a pretty good primer for you to just watch it, understand what you need to understand, and plow right on into doing your chemistry problems. But I will say that for those of you who don't know, I have already created I think it's 4 hours of unit conversions, a unit conversion tutor DVD that you can go look at on the website and get. And that has everything that I'm talking about here exploded up into even more detail. With a lot more problems to give you practice. So if there's any confusion at all on scientific notation, SI system of units, unit conversions, go get yourself a copy of the Unit Conversion Tutor because it extensively teaches you that stuff. And I cannot stress how important it is because when you learn how to convert units properly, you can almost do all of your problems without really thinking about what to do if you know how to do units properly. So let's start here at the beginning. For those of you, again, who don't know, we have the SI system of units, right? So for length, here in the US, we a lot of times talk about miles and inches and feet and things like that. But when you get into science, just throw out the idea of miles and inches and feet, and cubic feet and things like that. Just throw them out because we never use them in engineering, science, or anything like that. We're always on the SI system, which is called the metric system, right? So the unit of length that we're going to be talking about in chemistry, the base unit of length is called a meter. And I know you've heard of that before. And we abbreviate that with the letter M. A meter is pretty close to a yard for those of you who need something to help you visualize that. If you stretch your arms out like this, that's about a meter. It's just to give you kind of a ballpark estimate of how big that is. And this is the base unit here. All right. Now the unit of mass, which is how much of something we have, in your hand, how much of a quantity of anything you have. The base unit that we're going to always use is the kilogram, which is kg. Which we'll talk about how that's related to the gram here in a second. But basically, gram, kilogram, they're all in the same family. They're talking about mass. All right. Time, finally, something that doesn't change. We use the second. So, letter S. And for temperature, the SI base unit of temperature is actually something called the Kelvin, which is symbolized by the letter K. Now later on in chemistry, we will use the Kelvin pretty extensively. I mean, the Kelvin, just so you know, it's kind of interesting. 0 degrees Kelvin is when all atomic motion stops, When you say something has temperature, it means the atoms are vibrating. That's what it means. When you heat something up, the atoms are vibrating even more. When you cool something down, the atoms are vibrating less. So the Kelvin temperature scale is the absolute temperature scale. When you say 0 Kelvin, you mean everything stops. No atom is moving at all. It's not even jittering even a tiny bit. 0 degrees Kelvin is impossible to reach. It's impossible to get there. Even deep, deep space is not 0 degrees Kelvin, but that's the absolute temperature scale. Now we will use it some point later in chemistry, but most of the time we're actually going to use Celsius, which is the letter C. And Celsius is something you're probably more familiar with. Celsius is the scale where 100 degrees Celsius is a boiling point of water. 0 degrees Celsius is the freezing point of water. We'll never use Fahrenheit. I shouldn't say never, but it's rare that we would ever use a Fahrenheit temperature scale in chemistry or in physics or any other math and science. So these are the base units we're going to use. Meter for length, kilogram for mass, seconds for time, and mostly we're going to use Celsius for temperature, but the actual SI system of units calls for Kelvin to be the base, so just so you know that there. Now let's talk a little bit about metric prefixes. Let me change colors here a little bit. Let me talk about metric prefixes. Now let me give you a little secret. Everyone has heard of a meter, I think. Everyone's heard of a millimeter. Everyone's heard of a centimeter. Everyone's heard of a kilometer, right? See, the base word has meter in it, but all of these things in the front are just prefixes that sort of change what you're really talking about a little bit. That's why the metric system is so powerful and so useful, because all of the base units are the same, distance, length, time, and everything else. But we have all these prefixes that sort of change what we're talking about here. So when we talk about kilometers, we're talking about a large unit. A kilo of something is a large unit, right? We talk about milli or micro or nano. You might think of, teensy tiny little nanometer. That's a teensy tiny little thing. That's very, very, very small. So we're going to talk a little bit about these metric prefixes, because really the secret to understanding the metric system is all in the prefixes. So we have the kilo, which is a metric prefix, and what kilo means is 10 to the power of 3. And for those of you who are a little bit rusty on your algebra, 10 to the power of 3 means 1,000. So it's 1,000 of something. So if the base unit of length, let's talk about meters, is about this far, that's a meter, right? Then a kilometer is 1,000 meters. And that's the unit of what we call a kilometer. So a kilometer is really far. It's 1,000 of these meters, right? And that's another unit we call a kilometer. So in the English system, in the U.S. system, I should say, we have miles, and we have inches, and we have feet, and we have all these other things. We know that these different units are different lengths. We know that an inch is about that big. We know that a foot is about that big. And we know a mile is, down the road to the store. It's pretty big, right? But they're all different words, and they're not connected, and they're not multiples of each other very nicely. This is a nice 1,000 is a nice power of 10 multiple. So it's really, really nice to have that. We'll talk about how later when we talk about unit conversions. But in the metric system, everything is going to be a power of 10 related to each other. So it makes it really easy to work with. So take the time to understand it, because when you do, it will make your life easier. So to give you an example here, in terms of kilo, we say that 1 kilometer is equal to 1,000 meters. So when you read the word kilometer, this kilo here, just replace it in your mind with 1,000. So instead of reading it as 1 kilometer, read it as 1,000 meters. That's what you should say, because kilo means 1,000. It's like you substitute in or something. And so you put this here in your mind, you're reading 1,000 meters here. 1 unit of 1,000 meters, that's what that is. 1 kilogram is equal to 1,000 grams. A gram is a pretty small unit of measure, right? But when we're talking about a kilogram, it's 1,000 grams. So again, in your mind, you can take kilo and replace it with 1,000. So you could sort of, in your mind, you could say 1 unit of 1,000 grams if you were going to do that. Let's move along here. And let's talk about, instead of kilo, this is a pretty big unit. Kilo is large, right? It sort of sounds large even. What about centi? That's another unit or another prefix. And centi is 10 to the minus 2. See, this is 10 to the 3 for 1,000. 10 to the minus 2 is the same as 0.01, which is the same as 1 over 100. So for those of you who aren't sure about the algebra, when you have something raised to a negative power like this, it's exactly the same thing as saying 1 over 10 squared. That's what that means. 1 over 10 squared is 1 over 100. So when we say centi, it's the same as 10 to the minus 2, which is the same as 1 over 100, which is the same as 0.01. These are all the same thing. I'm just writing them down to show you here. So when we say 1 centimeter, which you probably already know, is about that big. It's much smaller than a meter. It's 1/100th of a meter. So it's a unit that's much smaller than a meter. Because it's convenient a lot of times, if I'm measuring something that big, to talk about centimeters. It would be cumbersome to talk about kilometers or even meters if I'm talking about something small. All right, so just to give you an example, if I were going to measure something like, this big here, it would make a whole lot more sense for me to talk about centimeters than for me to talk about kilometers, because that's a smaller unit there. So it's 1/100th here. Now, continuing on in the progression here, let's talk about millimeters, or milli. Let's talk about milli. The prefix milli means 10 to the minus 3, which is the same as 0.001, which is the same as 1/1000. So if I were going to use this guy, it would be, 1 millimeter, right, is equal to, let's say, 1/1000 of a meter. That's what this is saying. We can read this millimeter. You can read the milli as 1/1000, which is the same thing when we talked about kilometer, replacing kilo with 1000. So you can see there's these different prefixes. Some of them, like kilo, mean large multiples because we're talking about something really far away. Maybe we want to talk about the distance to another planet. We would talk about kilometers or even something larger. But if we're measuring the width of a human hair, we're not going to use kilometers or whatever. We might use millimeters, or we might even use nanometers or micrometers, which are even smaller little divisions. But you see how everything is done. Everything is a nice power of 10. Kilo is 1,000. Centi is 1/100. Milli is 1/1000. So the whole thing progresses like that. Now, let me write a little table for you, just to help you out. And you're going to probably find this in your book, but just to help you out. 10 to the 9 is giga, right? We represent that with G. You might have heard of gigawatts of electricity. That's a huge unit of power. That's 10 to the 9, right? That's a lot of zeros here. That's like a billion of something. That's giga. Then you have 10 to the 6, which is mega, which we abbreviate with M. So here we might have, just to give you an example, we might have a gigagram of something, or here we might have a megagram of something, right? Here we have 10 to the power of 3, which is 1,000. We talked about that. That's kilo, and we abbreviate that with K, so we might be talking about kilometers, right? Now, if we get down smaller, then we might have 10 to the minus 1, which is deci, which is D. So we might have a decimeter, for instance. Now, you don't honestly use deci very much at all. I'm just putting it here for completeness. You might see it in your book. 10 to the minus 2 centi. We talk about C of something, so we might have centimeters as an example. Then we go 10 to the minus 3 for milli. We might have a millimeter. So we've talked about those. But I keep talking about in terms of meters, but this could be millisecond. Probably a lot of you have heard about that. When you're timing a swimmer, you might measure his results in milliseconds because you're really interested in how fast he crosses the line, right? So you might have the minutes, the seconds, and maybe the milliseconds after that, to kind of as a fractional between seconds, right? So these things can be applied to any of the units. That's why we're talking about them here in general. If you go even smaller, you get to 10 to the minus 6, which is micro. Right? Now, micro, you can't use M again, small m. This is capital M, this is small m. You can't use M again for micro. So you actually have this little symbol, which is the Greek symbol mu. Right? So you kind of go up and then put a little U on it. That's basically what you have here. And so you might talk about micrometers or microns, another way of talking about that. 10 to the minus 9, we call nanometers, right? And we use the letter N, so that's nanometers. And this is kind of in popular culture. Nanotechnology, what does that mean? Doesn't mean anything big. Nanotechnology means incredibly tiny. Or maybe an iPod Nano, that's really, really tiny. So the prefix nano means really, really small. 1/1000th of a meter is what that is. And finally, the last one I'll put on here is 10 to the minus 12, which is pico. We use the prefix P. Maybe you have a picosecond. Picosecond is incredibly tiny. It's even less than a billion. It's 10 to the minus 12. So these are incredibly small fractions of a meter. A meter being what you're familiar with, about this big, right? So I don't think I have to say this, but just for completeness, this scale, as we go this way, we go to larger units. So this is the metric system in a nutshell. This is the Cliff Notes version of the metric system. We have prefixes like giga and mega and kilo to represent large units of a meter or a second or a gram or whatever. Kilogram, megagram, gigagram, okay, you can do that. And then once you get smaller to smaller divisions of your base unit, you have deci, which you don't use very much, and then you have centi, centimeters, millimeters, micrometers, nanometers, picometers. But they all apply to seconds. They all apply to time, length, mass, anything in the metric system. All right, so now that we know what the metric system really is, right, and now you kind of know how to interpret it. If somebody tells you they have 2 centimeters or 2 centigrams or 2 milligrams of something, if you get the drugstore, they tell you 2 milligrams of a certain drug every hour, you'll know that that's a fractional of a gram. That's what that is. Now that we understand that, I'm going to teach you, truthfully, from the bottom of my heart, seriously, one of the most important things that I have ever learned in all of my math and science studies, and I learned it, I guess I was in high school. I had a very good teacher who taught us this, and it honestly has saved me all throughout engineering, all throughout graduate school. It's something I constantly use. And here's the deal. When you try to convert units, you might be going from kilometers to micrometers, right? You might be going from gigameters to picometers. And if you're not sure what to do, you might know what the conversion factor is between these two things, but until you get some practice, you may not know how to set it up. Do you multiply by 1,000 to get what you're looking for, or do you divide by 1,000? Now, you can mentally do the gymnastics and figure it out, but early on, when you're getting used to this stuff, it's kind of complicated, and you can lead yourself down the wrong path easily. So what we're going to do here is a few quick, simple examples of unit conversions to show you how this works. Well, let's go ahead and do that. So what if you wanted to convert 500 meters to the unit of kilometers? So we know we know how far we have here. We have 500 meters of something, but we don't want to express it as meters. I want to express it as how many kilometers do I have. So what you need to realize is that you know the conversion factors in the metric system. That's really nice, is that a lot of times you know what the conversion, you don't have to memorize what it is. If you were in the English system, you might need to know that how many feet are in a mile. 5,280 feet are in a mile. That's a weird number. It's nothing, that's a nice magical round number. How many inches are in a foot? There's 12 inches in a foot. Okay, great, but that's not a nice round number. You have to remember a lot of those things, right? The metric system, everything's a nice multiple of 10. So it's easy to remember that in 1 kilometer is equal to 1,000 meters. How do you remember that? Because the prefix kilo means 1,000. 1 kilometer, 1,000 meters. That's what it is. If you memorize these prefixes, which you're going to do naturally as you study any of this stuff, then this becomes important. So you know what the conversion factor is to go back and forth, but in the beginning here, you're not really sure. Do I multiply or divide by 1,000? And this is a super simple problem, I'll give you that. So a lot of you may look at this and know what to do, but I guarantee you as you get farther in chemistry and you start working with density and grams and later on moles and molarity and cubic feet and other things and cubic meters, as we start doing these things, then it's going to become really, really useful what I'm about to show you. How do we convert these two things? First thing you do is write down what you know, 500 meters. That is what you know. So you write that down. Always start with what you know. Do not start with the conversion factor. So you write down what you know. You draw a horizontal line here and a vertical line here. So you're kind of doing like a little, almost like a tic-tac-toe or something. So you draw this line here and this line here. The next thing you want to do is you want to write your conversion factor that you have right here. This is sort of like a fraction bar, a giant fraction bar. We'll talk about that here in a minute. Now, what we know is that 1 kilometer is equal to 1,000 meters. So what we want to do is write it like this. We want to write it like this. 1 kilometer is equal to 1,000 meters. Now we want to write it this way because what we're going to do is we're going to treat this like a fraction, because it is a fraction really. This is like a fraction bar. So you see how we have meters on the top and meters also on the bottom here? What this allows us to do is sort of cancel the meters with the meters. In effect, what they're doing is they're dividing out. It's like, you know, anytime in a fraction, if you have 5 divided by 5, they divide out, they give you 1. Well, here we have meters divided by meters, so the units cancel like that. They sort of disappear. So the final unit that we're going to have is not going to be meters because these have canceled. The final unit we're going to have is kilometers, which is what we want. We're trying to convert to kilometers. So what we do here is we treat it like a fraction. So what we have is 500 times 1. We're multiplying by 1 because these are both on top. We take the result of that, which is 500, and we divide it by 1,000. 500 times 1 divided by 1,000 is going to give you 0.5. 0.5 what? Well, the only unit remaining that hasn't canceled with anything is kilometers, so we have kilometers. This is the answer. Now, this is something that you could do in your head because I made up an easy problem on purpose so you could follow it. 500 meters, if you know that 1,000 meters is a kilometer, then 500 meters must be half a kilometer. That's really easy. But I guarantee you I could generate a problem that would involve nanometers or picoseconds, and I would confuse you on what to do. But if you set it up this way, where your units cancel, leaving you with the unit you're trying to convert to, you will always get the right answer, and you won't even have to decide to multiply or divide. That's what the real power of it is. You don't even have to think about the logical thing to do to multiply or divide. All you need to do is set it up properly so that in the end, you'll get the unit you want. Now let me show you one more thing real quick before we move on to the next problem. What if we set it up the other way? 500 meters. Now the next thing we need to do is write our conversion factor. Let's just say you took a guess and you wrote it this way. 1,000 meters is equal to 1 kilometer. You were getting ready to do your stuff here, and then you would look at this and you would try to cancel it, and you would notice, okay, meters and kilometers, they don't cancel, because these are different units. Now these guys are the same on top, but they only cancel if they're in the top and the bottom. They only cancel if they're in the top and the bottom. So if you accidentally wrote it this way, you would immediately catch your error, because you would look here and you would say, kilometers doesn't cancel with anything else, so I can't do anything. So this is totally wrong. So you would discount that right away because you're not left with the unit you're trying to convert to. All right. Now what if you were trying to convert 4 centimeters to meters, right? So you would do it exactly the same way. You start with what you know, 4 centimeters. Draw your little horizontal and vertical bar, and next you have to write down the conversion factor you know. How many centimeters are in a meter? There are 100 centimeters in a meter, so you write it this way, 100 centimeters in 1 meter. Why do you write it that way? It's because when we write it this way, as opposed to if it were flipped, the centimeters will cancel with the centimeters. So they're gone. The only thing I'm going to have left is meters, which is what I'm actually trying to convert to. 4 times 1 is 4. 4 divided by 100 is going to give me 0.04. The unit is meter, because that's the only thing left over. That's what I'm trying to convert to. And we'll do a few more little simple problems, but I guess I'm just going to cut to the punchline here. This little method works for anything. Any unit at all. Anything. Physics, chemistry, math, biology, anything at all with a unit. If you're talking about meters per second and you're trying to convert it to kilometers per day, you can do that. If you're trying to take grams per cubic centimeter and convert it to kilograms per cubic kilometer, you can do that. All with this method here. And you don't have to think about what to do. You just set the units up so that everything cancels. Make sure your conversion factors are correct. Outspits the correct unit because that's the way you've set it up. Now let's say we're going to do something a tiny bit more complicated. Not really, really complicated, but a little bit more. What if I were going to convert 4 centimeters? Instead of to meters, what if I wanted to know how many millimeters that was? right? So a lot of you looking at this may not know what to do. Some of you probably do know what to do, but a lot of you, I bet you don't, because you have 4 centimeters, and unless you're good with the metric system, you may not know off the top of your head how many centimeters or how many millimeters are actually in a centimeter. A lot of you may know that watching this right now, but some of you don't, so I'm not going to tell you because I'm going to pretend that we don't know. But we don't know how many, let's pretend we don't know how many millimeters are in a centimeter. But what we do know is how many, we know, I'll write down what we know. What we do know is 1,000 millimeters is equal to 1 meter. And we also know that 100 centimeters is equal to 1 meter. But this isn't exactly where we're trying to go, because we're actually trying to go from centimeters to millimeters. But we don't actually have a conversion factor. You may know, okay, right now watching this, you may know how many are in there. But we're going to pretend that we don't know. But what we do know is how many millimeters are in a meter and how many centimeters are in a meter. So let's just use what we actually have here, and I'll show you the power of this method. If you write it this way, 100 centimeters in 1 meter, right? I can continue this guy as many times as I need, and I can write it like this. 1 meter is 1,000 millimeters. Now, why did I do that? Because right here, centimeters cancels with centimeters, and meters also cancels with meters. Anything in the top is going to cancel with the same unit in the bottom. And you can extend this unit conversion thing as long as you need to get the units to cancel in the way that you need them to cancel. So you've canceled the centimeters, you canceled the meters, all you've left is millimeters. So the way you do this is 4 times 1 gives you 4. 4 divided by 100. Take that, multiply by 1,000, divide by 1. So basically what you're doing is everything is multiplied together in the top, and then you divide by everything on the bottom. That's all you're really doing here. The answer you're going to get is 40 millimeters. 40 millimeters. Now, for those of you that did know, 4 centimeters, how many millimeters are in a centimeter? A lot of you probably already knew that 1 centimeter contains 10 millimeters. This is not something I've told you. This is something that some of you may know just because you may have worked with the metric system a little bit longer, and that's okay. So if you happen to know that that's your conversion factor and you know that to be a fact, then, and look at what I've done. I've flipped it wrong, upside down. It's a good example of how you can catch your mistakes, right? So what we know is 1 centimeter is 10 millimeters, right? The reason I caught my mistake is because I looked down to cancel my units and I couldn't do it, but now I can cancel centimeters with centimeters. So all I have to do is do 4 times 10, of course, divide by 1. I'm going to get 40 millimeters. But do you see the power of this? I mean, I don't know if it dawns on you yet, but it should, because it's very powerful. I've done the problem 2 different ways. One way, I knew the direct conversion factor between the 2 things I was trying to do, and I get the right answer. Here, I didn't really even know the direct conversion factor. All I knew is 2 different conversion factors. In other words, I connected centimeters to meters, and then I connected meters to millimeters. So you can sort of think about it as a connect the dots. If I'm trying to convert from one unit to the other, I don't need to know a direct conversion factor between the 2. If I know it, that's great, wonderful, use it. But if you don't, just as long as you connect the dots with your conversions from point A to point B, you'll always get the right answer. Here we went from centimeters to meters, meters to millimeters, and we get the right answer. I'm telling you that as you do this more, in chemistry and other classes, it will save you on so many occasions because it really prevents you from getting in the mental entanglement of figuring out what to do. Now, what if I gave you a problem and I said, given 1 inch is equal to 2.54 centimeters? Right? That's something that I haven't told you up till now, but it's true. If you measure an inch, it's 2.54 centimeters. And what if I asked you to convert 2 inches to centimeters? How would you do that? Well, I've given you the conversion factor, so all you do is you start with what you know, 2 inches, and now we apply our conversion factor. 1 inch is equal to 2.54 centimeters. The way I write it is 1 inch is 2.54 centimeters. I don't flip it over because if I flipped it over, I wouldn't have any units canceling anywhere. But here I have inches cancel with inches, which leave me only with centimeters. 2 times 2.54, divided by 1 obviously, is 5.08 centimeters. And that's the answer. And that's basically it. I'm just giving you a few really easy examples here. I'm not going to go into density calculations. I'm not going to go into other things because really we're going to use this technique here all throughout the course. In almost every problem we do, you'll see something like this because we'll be setting up our units. And I'll also tell you, if you want more of a background in SI system, unit conversions, things like that, go look at the unit conversion tutor. It's 4 hours of all of this stuff, giving you lots of different units, lots of different examples. I think what I've shown you here is good enough to kind of get you primed, and as we go through the course, we'll do it together and you'll learn, and I think it'll be okay. But for those of you who want a little extra, go take a look at that because it's all in there. All right. Now, one more thing I want to talk about before we leave here is scientific notation. It's something a lot of you may have already seen before. Maybe it's totally, completely new to you here. But it's a very simple concept. Don't let the name scare you. Scientific notation. Oh my gosh, it must be so incredibly difficult. It's very easy, actually. What basically amounts to is numbers are great. I can represent, 127 apples if I want to. And that's easy. It's just 3 digits, 127 apples. But what if I had, 5 billion apples? What if I had 5,342,592,394 apples? Well, I could write all those digits out, but that gets really annoying after a while. What if I'm even doing something larger? What if I'm measuring the number of meters or kilometers to the nearest planet or to the sun? We're talking millions or even billions of kilometers away. So it's just a lot of digits to write over and over again. So there's a shorthand way of writing very large numbers and also very small numbers. So, if you're looking at the size of a molecule, you might be talking about 10 to the minus 9 or very micrometers or something like that. So we use a different way of writing very large numbers and very small numbers, and that's called scientific notation. The easiest way to explain what it is just to show you. What if I had the number 2376, 2,376, and I wanted to represent that in scientific notation? The way I would do it, I would keep the same digits, 2.376. Digits are the same, but I put a decimal point after the first digit. And I multiply by 10 to the power of 3. Why do I multiply by the power of 3? It's because if I put the decimal here, then when I multiply by 10 to the 3, basically you move the decimal as many times as is indicated in this exponent. So I move the decimal 3 times. 1, 2, 3. 2,376. So it's basically a shorthand way of writing that. And you might look at this and say, well, this looks shorter. I mean, what's the big deal about doing this? Well, as you use this more, you'll understand the advantages of it. What if I have 151 and I wanted to convert that to scientific notation? It would be 1.51 times 10 to the power of 2. Now, where this comes in handy a lot of times is, what if I were measuring the distance to the sun or something? What if it came out to 2,374,938,721? And that's a number of kilometers. Well, that's a lot of digits, right? Obviously, every digit is important, but probably mostly what you're interested in is the kind of general order of magnitude of it. And the last digits over here, yeah, they're important to be exact, but really when you're talking about the distance to Mars, you may not care about every last digit there. So the way to really handle that is you could write this as 2.3749. Let's say you wanted to take it out to here, but then you would multiply by 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9. Because in scientific notation, the decimal is here, but when I multiply by 10 to the 9, it's just moving the decimal. Let me ask you something. What happens when you multiply something by 10? Let's say you have 4 and you multiply by 10. What happens? Well, that's 40, right? All you've done, see, there's a decimal point here. You can't see it because it's 4.0, but the decimal's here. If I multiply by 10, I move the decimal on the other side of that little invisible 0 here, making 40. What happens if I multiply by 4 times 100? Right? Well, I'm going to get 400. What happens if I multiply 4 times 1,000? Right? Well, I'm going to get 4,000. You see, every time I multiply by a bigger, multiple of 10 like this, I'm just moving the decimal point one spot over to the right. That's all I'm doing. So if the decimal is here, I move it one spot, I get 40. The decimal's here, I move it 2 spots, I get 400. Decimals here, I move it 3 spots, I get 4,000. So this is 10, this is 10 squared, this is 10 cubed, right? So this is 10 to the 9th. 10 to the 9th just means move the decimal place 9 spots that direction. That's all it means. So all you have to do when you're looking at scientific notation of something is look at this exponent to the right that many spots. Now, yes, this answer that you get is not going to be exactly the same as this because I've truncated, I've left off some of the digits. But when you're talking about really, really long distances, that's good enough for most cases. All right, now let's look at a different example. What if we have something small, 0.0023? How would I write that in scientific notation, 0023? Well, if I use positive numbers to make me move the decimal point to the right, then what I'm going to end up doing is using negative exponents to shift the decimal point the other direction. So the way you do it is you look at your first numbers here. Here you have the first number other than 0 is 2 and 3, so we have 2.3. Always put the decimal after the first digit times 10 to the minus. Pretend you have a decimal point here. You're going to move the decimal to the left 1, 2, 3 spots. 10 to the minus 3. And this is really where it shines also because, this is kind of ugly, 0.0023. What if you have 5 zeros, 0.00023? Well, this is going to end up being shorter to write, and it's just something you're going to have to learn. And you'll see a lot of your problems that will express number of grams in terms of scientific notation, so you'll have to understand. What if we have 3.12 times 10 to the minus 5. How do we convert that back to a regular number? Well, we have a negative decimal here. So my advice to you is just to write down your numbers, 312. Stick your finger right here where the decimal is, right here, and then you're going to have to shift it to the left 1, 2, 3, 4, and put a decimal point here, and just check yourself. Put your decimal point here and shift it to the left 5. 1, 2, 4, 5. And you could put a leading 0 here if you wanted to. 0.0000312. And I can't tell you how many times I've actually written a number and stuck my finger there and counted the decimals. And you're just going to have to do it. That's just the way it is. But if it's the critical thing to pull out here is if your scientific notation has a positive exponent, you're shifting the decimal point to the right. You're making a large number. If it's a negative exponent, you're shifting the decimal to the left, which means you're making a really small number. One final example is how would I write that as a regular number? Well, I just write 5, 4. I stick my finger there and I start writing zeros. 1, 2, 3, 4, 5. I check myself. I stick a decimal here and I move it 6 spots to the right. 1, 2, 3, 4, 5, 6. And that's what I came up with. So frequently you might kind of put one less 0 or whatever, check yourself, and then you have to add a 0 to make sure. But this is what this means. 5.4 times 10 to the 6 is the same thing as 5,400,000. And that's a good intro to scientific notation. And again, I'll just say it one more time. If you need more practice with scientific notation, if you aren't quite sure, if this isn't enough for you, go look at the Unit Conversion Tutor. It has a whole section on scientific notation with a lot of different problems. I think, again, this is enough to get you by, especially if you've seen it before. And we're going to be working with it so much that you'll probably get really comfortable with it here quickly. But if you need some extra help, Unit Conversion's there, 4 hours of concentrated coverage of that. So we have covered another section. We've talked about the really important topic of units and unit conversions in chemistry. We've talked about the SI system. We've talked about the metric prefixes. We've talked about what they mean. We've talked about converting units and showing you, I don't really want to call it a trick. It's not my trick. A lot of people use it. But unfortunately, a lot of books don't show you how to do unit conversions in this way. And I'm telling you that this will save you so much time when you get to more complicated units. Your mind will just spin with how easy it is after that. And occasionally you might bump into one of your friends that has never seen this before, and it'll save their, save from pulling their hair out, when they're doing their homework as well. We've also talked about scientific notation. measuring, or I should say writing down large numbers and also very small numbers. A lot of your problems, you'll see the number of grams or the number, or the distance of something, or the amount of something in terms of scientific notation. So you just need to know it's just a different way of writing a large number and a small number. And you can input scientific notation directly into your scientific calculator or your graphing calculator. So you just type it in just like you see it, and you can use it there. My name's Jason. I hope you've enjoyed this section. I hope you've learned a little something here. Stick with me. I'll take you step by step here in the next few sections. We're going to start talking about some real chemistry, putting elements together to create compounds, and then going and looking at chemical reactions. But we need to do things one step at a time. The most important thing you can do for yourself is go in order. Watch everything in order, absorb everything. If you try to skip around too much, then you're just going to be confused for no good reason. I'm Jason. Practice your problems. Practice your unit conversions. I promise you it'll save you a ton of time on your homework and on your exams.